fact that quantum entanglement, Einstein's spooky action, helps the European robin navigate its way down to warmer climates every fall, has a certain romance to it. I would like this to be the correct theory. Of course, liking something, wanting it to be the correct theory, doesn't mean it's the correct theory.
Mm-hmm.
But it's a fun, interesting application of one of the weirder features of the quantum world, quantum entanglement, playing an important role in a living animal, helping it find its way.
Hello, this is Robinson Earhart here with Pins podcast and the introduction to Robinson's podcast number 185. And this episode is with Jim Al-Khalili, who is University of Surrey Distinguished Chair in Physics and University Chair in the Public Engagement in Science. And Jim is a theoretical physicist, lots of work in physics. He's an author with lots of books and a broadcaster with lots of documentaries. And in this episode, we talk all about the fundamentals of quantum biology. That's his current project and what his group is working on at the University of Surrey. We talk about just what quantum biology is, since if the world is quantum mechanical, then biology must be too. We talk about how some animals, like the robin, which is my namesake, might take advantage of quantum mechanics, how some exotic phenomena like quantum tunneling and decoherence might fit into the biological world, how quantum mechanics relates to the numerous arrows of time, and then we also get into Jim's personal favorite interpretation of quantum mechanics, because it's pretty hard to have a conversation about QM without talking about the interpretations and theories as well. Jim's latest book is The Joy of Science, and there's a link to that in the description. I will also mention the Patreon. If you would like to support the show, that is a great way to do it beyond leaving reviews, subscribing, comments, that sort of thing. After 4 Patreon episodes now, or episodes, since the Patreon has been up, I've decided to jettison for the time being transcripts, since people don't seem to be that interested in them and they take a lot of work just to do poorly. So there is a link to ad-free episodes and then show notes. Now, without any further ado, I hope you enjoyed this conversation as much as I enjoyed having it with Jim. In 2014, you and John Joe McFadden published Life on the Edge, which, as I understand it, is the first popular book on quantum biology. But when we were talking before recording, you told me that quantum biology is also your current project, nine years later. So what's going on at the University of Surrey right now?
Well, we're hoping it's becoming sort of a hotbed center for research in quantum biology. Admittedly, a subject that is still sort of quite niche and probably speculative and even controversial, maybe some would say. Actually, that my collaboration and discussions on whether quantum mechanics plays a role in biology with John Joe McFadden, who's a molecular biologist, I'm a theoretical physicist, actually goes back to the late 90s. The story is that John Joe came to, so he's based at Surrey with me as well, but he's in the life sciences school. He came and gave a seminar in the physics department on whether quantum mechanics might, speculatively play an important functional role in biology. And most of my colleagues dismissed it. I decided that I'd want to chat to him a bit more about it. It sounded intriguing. And so we've been dabbling with it since then. 2014, we published the popular science book on it. As you say, Life on the Edge. Still, I think, the only popular science book on quantum biology. But by that point, we had started to get a bit more serious. So my background in theoretical physics and nuclear physics was, I was ready to shift my interests, and John Joe likewise. And so, we got funding, we got grad students, we got research grants. And today it's something that I'm actually, sort of some fraction of my research activity is looking seriously at these quantum effects in biology.
Hmm. Yeah, you mentioned immediately that it's very niche, and I should add that relative to fields like quantum mechanics, which have had time to get into the zeitgeist, it's still quite nascent. So
Yeah,
I think it would behoove us to start out with just some of the basics. And
sure.
if we live in a quantum mechanical world, then isn't all biology quantum? So what distinguishes the sorts of problems and approaches in this field from the more familiar dimensions of biology?
Yeah, I mean that's a good point, and it's something that people sort of that's the most people's initial reaction. You know, everything is made of atoms, and so if atoms obey the rules of quantum mechanics, then of course, you know, at some point, if you dig deep enough, life will also obey those rules. That's not what's meant by quantum biology in this sense, and we have to be careful because it treads this um, not dangerous, but rather controversial path, because as soon as you start talking about quantum mechanics and life, you know, those who probably haven't studied quantum mechanics very quickly think, oh, okay, so that you said quantum mechanics explaining consciousness, or quantum
Mm.
mechanics, you know, will explain all sorts of wacky woo-woo stuff. You know, oh, it explains telepathy and homeopathy. Telepathy is the favorite one because quantum entanglement. Oh, that's why twins can. So you sort of have to sort of draw back from that. Physicists and chemists have been used to quantum mechanics. We've had almost a century now, and you know we use quantum mechanics every day. Without it, we wouldn't have developed much of our modern world. Um, Biologists have, by and large, not worried or bothered about quantum mechanics. The point about quantum biology is not that down at the level of the chemical bonds that hold biomolecules together inside living cells must obey some sort of quantized rules. Yet, of course, but that's chemistry, right? And the chemist will say, "What's all the fuss about?" It's more that there seems to be evidence that there are certain processes, quantum processes, that take place inside living cells, quantum tunneling, quantum entanglement, long-lived quantum coherence that are
Mm.
unexpected, right? You know, because the usual argument is, hang on a minute, quantum mechanics is, you know, quantum effects are ephemeral, they're very delicate. We work hard to maintain quantum effects in our physics laboratories. We're trying to build quantum computers that don't, you know, decohere very, very quickly. You're telling me inside a hot, noisy, complex living cell, these quantum effects can play a functional role? Well, it seems like the evidence suggests that yes, maybe they do. And for me, that, I mean, it may not be, may turn out to be complete red herring, but for me, it's so fascinating and so interesting that it's a worthwhile thing to do to study it carefully to see what the truth is.
Hmm. Well, I actually, in a relatively, just going back to the first thing you said, in a relatively recent podcast, I just learned that quantum Bigfoot is a thing. So there are no
Wow.
limits to which quantum terminology can be applied. But
Yeah, it's a worry. I mean, I blame a lot of the physicists in the late 60s, early 70s who were all high on LSD. And all, you know, they thought, you know, quantum weirdness was became almost like a cult mythical connection with Eastern mysticism, and was trying to shake that off. Quantum mechanics is a serious description of the subatomic world.
Mhm.
And if life has evolved the ability to maintain quantum coherence for long enough so that it plays a role, such as the sort of work we're doing now looking at proton tunneling in DNA, then, you know, we need to try and model that and study it and carry out experiments to test if it's true or not. But these are very
Mm.
isolated, specific examples where quantum
Mhm.
mechanics plays a role. It's not, we're not saying life doesn't exist without quantum mechanics, but life may have evolved the ability to use the trickery of the quantum world. And why wouldn't it if that gave it an advantage?
Right. Absolutely. I'd like to hold off on the tunneling, the entanglement, and
Sure.
coherence, which latter phenomenon I understand is quite important to your current work on the arrow of time, just for the moment. Because
Mm.
first, there were some interesting conceptual difficulties that I encountered when I was reading your work and preparing for this, and I was wondering what some of the technical difficulties are that come with the territory of blending quantum mechanics and life. So I saw that there were, I mean, specific difficulties involving studying quantum processes in living tissue.
Yes, it's all very well, theorists like me working with computational chemists and running computer simulations, um, uh, deciding that we want to look at a simple process. So you isolate it, the spherical cow in a vacuum business.
Mm,
Um, Physicists are used to being able to isolate the mechanisms and phenomena they want to do. We want to study. In a laboratory, we will turn things off. We will run our experiments near absolute zero in a vacuum. We'll shield it from its surroundings, and then you tweak dials. You look at one variable at a time. You can't do that inside a living cell because there are thousands of biochemical reactions going on. So the experimental tests that would verify some of these theoretical predictions and model predictions are subtle and sometimes indirect. And I think that's why in quantum biology, theory is ahead of experiment. One can study biomolecules using various spectroscopic techniques. You can use, sort of high pulse lasers to excite these molecules and watch how they decay and give the light off, and there'll be certain signatures in terms of resonant behavior that could tell you something about the quantum nature of these molecules. But it's tough, it's difficult to turn off everything else inside a living cell to isolate the mechanism you're interested in. That's where the challenge is.
hmm Yeah, I mean, talking about lasers, I recently did an episode with the Nobel laureate here at Stanford, Carl Wyman, on his isolation of the Bose-Einstein condensate and
Right.
reducing cellular cells to temperatures just above absolute zero. They're not going to function too well
No,
at
no.
that point.
Yeah, I mean, the nice thing is, of course, that essentially what got a lot of people interested in the field is Schrodinger's famous book "What Is Life," written back in 1944. A small book, almost like a popular science book. It certainly was in his ideas influenced Crick and Watson in their development of the double helix model of DNA. But he makes this, simple statement that sticks with me anyway, which is that life, the order, the structure of life, of inside a living cell, is reminiscent of inanimate matter of equivalent complexity near absolute zero. So you
Hmm.
take inanimate matter, certain materials, you cool them down to a few degrees Kelvin or below, and you are calming down all the thermodynamic
Right.
chaos, slowing everything down, and you start to see quantum effects, superconductivity, superfluidity kicking in at certain temperatures. Well, Schrodinger was arguing that living systems behave, in terms of the low entropy, high order, the structure, as though it's normal matter at low temperature. So it may be that we don't need to cool down living systems down to near absolute zero. They are exhibiting the sort of structure and behavior anyway that you would see in inanimate matter that's very cold.
Hmm. I don't want to jump too far ahead, but is this line of reasoning, was it influential to you in beginning this work on the arrow of time and life? I mean, life somehow, I mean, at least locally, seems to counteract entropy to some extent.
Yes, I mean, I think a lot of physicists and chemists and philosophers, there is something about the mystery of life that is sort of intangible, but it's fascinating. There was a recent paper in Nature uh, um, on what's called assembly theory. It is a new idea in chemistry that it works out the likelihood that chemistry can become biology. What's the probability that you can get complexity emerging from simple building together simple atoms and molecules? And I think the excitement there is that we have to admit we still don't know how chemistry becomes
hmm
biology. The origin of life, despite some people arguing, well, it's a step by step process, and it's not Fred Hoyle's famous a wind blowing through a junkyard and creating a jumbo jet, just instantaneously. It's a slow process, but there is still something mysterious about it, and I guess that is part of the attraction. You do wonder, did quantum mechanics play a role, say, in prebiotic chemistry, in the origin of life? I have no idea if it did or not, but that may have been, I guess, in answer to your question, one of the
Yeah.
factors that maybe got me excited in the first place, even if we've now sort of pulled back a bit and trying to look at it more soberly and carefully.
Hmm. Yeah, that's interesting. I never thought of it that way. Like, I'm sure many people, I first encountered, the problem of how life emerges from raw materials in Dawkins' selfish gene.
Yeah,
And as I recall his description of life emerging from the primordial ooze or soup, it's really, maybe it's kind of like a mechanical
yeah,
thing. And I'm using mechanical and distinct from quantum mechanical.
yes,
But so it's
yes,
interesting to think that quantum mechanical phenomena might have played a
yeah.
role there.
I think we know now that it's more than just stick all the ingredients in Darwin's warm pond, or
Yeah.
the famous Miller-Urey in 1950s experiment. Organic materials, water, sunlight, the spark of life would emerge. The likelihood of that happening is still hugely, hugely tiny, and so there's still something missing, getting us to
Hmm.
a complex enough system that is able to replicate itself.
Hmm.
Once it does, Darwinian evolution kicks in, and you're well on your way. But it's how do you get there in the first place?
Well, now that we've set some context, but before we get to the era of time, I think that quantum biology, as we already mentioned, is going to be very unfamiliar to our listeners. It wasn't something that I'd thought much about at all before this. So I thought it would be a good idea to talk about a few examples. And the first that comes to my mind is it's actually what you begin life on the edge with is my namesake, the robin. And
Mm.
from the outside, these birds, certainly seem to inhabit the classical world that we do. But where do quantum processes come into shape their observable behavior?
This has become sort of the poster child of quantum biology,
It's a good
just
place to
because
start then.
it's so fascinating. Yeah.
Hmm.
um, so the European robin, which essentially lives its spring and summer up in northern Europe, Scandinavia, Sweden, Russia, and every fall it will migrate down to the Mediterranean looking for warmer weather, as many animals, marine mammals, birds, insects do. In a similar way that, for example, monarch butterflies will migrate every year from northeast Canada, eastern Canada, down to Mexico. Um, in the 1970s, it was established that the European robin, that was, I think, the first creature that was confirmed to have this ability, that it was able to utilize, among the many tricks that migrating animals use to navigate, it was able to sense the Earth's magnetic field, the angle of inclination of the magnetic field. So if you think about the Earth as a giant dipole magnet, the magnetic fields emerge vertically from the north and south magnetic poles, and then around the equator they're parallel to the ground. And so the bird in flying is able to sense the orientation, inclination of the magnetic field. There's a famous ornithologist couple in Germany, the Wilczkos, who would capture these robins in mid-migration and put them inside these little sort of containers, sort of cone-shaped, that have blotting paper, ink at the bottom and blotting paper up the side. So when the bird is at the bottom, it gets ink on its feet. And as it tries to fly to escape from these containers, it tends to want to fly out in the direction to continue its migratory journey. And so this is how they established that it was actually wanting to fly in that direction. How do they know it's a magnetic effect? Well, they would put they put Helmholtz coils, giant sort of magnetic coils, on either side of the trap containing these birds, and they could have these coils in the reverse polarity to the Earth's magnetic field, with the same field strength. So when you turn them on, they cancel out any magnetic field. And when they do that, these birds fly randomly in all directions. As soon as they turn off the magnetic fields, the birds sense again the Earth's magnetic field, and they want to fly in a particular direction. So there was a famous paper in the 1970s in the journal Science that established that these birds, and later other marine mammals and insects, have a built-in compass, some chemical compass somewhere in the body that gives them directional information. Of course, the mystery was, where is this compass? How does it work? Now, here we are, 2023, and the only theory in town, the only theory that has survived, that is still in play, is the idea that quantum entanglement is playing a crucial role. So quantum entanglement, the idea that two separated particles are part of a single system. However far apart they are, you have to describe them as a single quantum state, which means that affecting one of them will influence the other. It was also established that this chemical compass, however it worked, resided in the bird's retina because it was light activated. And so,
Right.
even there's a researcher in Germany, in Ulm, who designs these experiments where he covers these birds with, a bit like the executioner's mask that sort of covers the eyes. And once these birds can't see, they also can't sense the Earth's magnetic field. So it's triggered by photons entering the bird's eye. None of that is controversial. That is all sort of pretty well established science. Of course, what's controversial is, how does it work? The theory is, in quantum biology, that photons enter the eye. A photon will knock one of a pair of coupled electrons in an atom within a protein molecule called cryptochrome that sits in the back of the retina. The photon knocks one of these electrons off, so it sort of gets knocked off and it sits on an adjacent atom, still within this large protein made of, thousands and thousands of atoms. But these two electrons remain quantum entangled, which means that the way they spin, whether they're both spinning up or one spinning up, one spinning down, the way they spin is very sensitive. The way they dance together is very sensitive to their orientation in the Earth's magnetic field. So even though it's very, very weak, it has the ability, to influence this delicate, entangled state of these two electrons. And then when they collapse, when entanglement disappears, that sends certain messages to the bird's brain, telling it the orientation in the field. What's fun about this is that quantum entanglement famously was a phenomenon, a mechanism in quantum mechanics that Albert Einstein hated.
Right.
He called it spooky action at a distance.
Mm-hmm.
We are beginning to appreciate that quantum entanglement, and as part of my research at the moment, is a fundamental feature of reality. Fundamental that I feel we should be teaching undergraduate physics students about quantum entanglement. It's not really something they encounter in standard undergraduate textbooks yet. But the fact that quantum entanglement, Einstein's spooky action, helps the European robin navigate its way down to warmer climates every fall, has a certain romance to it. So I would like this to be the correct theory. Of course, liking something, wanting it to be the correct theory, doesn't mean it's the correct theory. Mm-hmm. But it's a fun, interesting application of one of the weirder features of the quantum world, quantum entanglement, playing an important role in a living animal, helping it find its way.
Mm-hmm. Just a completely tangential comment. We can imagine what sight or smell are like for birds, but I wonder what it must be like to sense magnetic fields. And especially,
there's a paper that suggests that what the bird sees is like some sort of dark patch imposed, like augmented reality on its field of vision, and it tries to centralize that, like a pilot trying to get the crosshairs in there when they're flying in a plane.
I guess since you described this theory as or this process visually, I mean, it's taking place in the retina, it would make sense that maybe
Yeah,
they would experience it phenomenologically
exactly.
as
Yeah, yeah.
visual phenomenon. But would this also just came to my mind, but would you anticipate that, and maybe this experiment has been done, that if you moved these birds to the southern hemisphere, they would just instinctively start migrating in the exact opposite direction? Or is it sensitive to the polarity in it?
No, I think that's right. I mean, I'm not sure if anyone's done the experiment, but there may be other animals that have this magnetoreception, this sensing the Earth's magnetic field. But that would certainly be the implication. You know, wherever they are, if they're near the North Pole or the South Pole, their directional information will be towards the equator, towards the direction where the magnetic field is more parallel to the ground. So they don't care which hemisphere they're in. It should be the same thing, moving towards the equator.
Hmm. And you also said that I think this is just the only theory that's in town at this point, and it seems like it's very well formulated. But am I to take it that it hasn't been experimentally confirmed, and then would that be because of the reasons we sort of discussed earlier, where it's very difficult to do these experiments in vivo?
Yeah, absolutely. I mean, all you can do is experiment in vitro on individual protein molecules, the cryptochrome
Yeah,
molecules,
yeah, yeah.
and so you'd have to hit them with a laser pulse or something like that, and see if you can get some sensitivity to magnetic fields uh, for the molecule sitting by itself.
Hmm.
Whether that's enough of a smoking gun, if that result confirms that there is a sensitivity, it may convince some, but others may be harder to be persuaded.
Well, just to round things out, you also mentioned quantum tunneling earlier, and
Mm.
quantum tunneling in close to 200 episodes has never come up on the show, and there have been a lot of episodes on quantum mechanics. So just what is quantum tunneling, and then where does it fit into certain enzymatic reactions?
Yeah, so quantum tunneling is a feature of the quantum world that we've known since almost the beginning of the birth of quantum mechanics. It's the way we explain radioactive decay. A particle, say radium or something, that's a nucleus that is radioactive that spits out an alpha particle. That alpha particle shouldn't be able to escape the nucleus. What it has to do is punch through an energy barrier, what's called the Coulomb barrier. Um, we now know that quantum tunneling, is everywhere. It's the reason why the sun shines, because two hydrogen atoms or two nuclei of hydrogen atoms, two protons, shouldn't in just described in classical mechanics without any quantumness, should not be able to get close enough together to stick in the first step towards thermonuclear fusion, which is what gives the sun its light and heat. Because two protons are positively charged electrically, so they repel. So there's a barrier that stops them from getting too close. But because in the quantum world, these things aren't really discrete particles, they are spread out waves.
Hmm.
They can leak through these energy barriers. I always talk about it it's like a ghost or phantom passing through a solid wall. There's a certain probability that these two protons can, or think of one staying where it is and the other getting through the energy barrier. Once they get close enough, then the strong nuclear force, which is an attractive force at very close distances, kicks in and they bind, and then you get the process of hydrogen, the first step of hydrogen becoming helium in fusion. But it's a strange effect. It's a bit like kicking a soccer ball up a hill. You've got to give it a big enough kick to get it over the hump of the hill. In the quantum world, you could kick it halfway up and it still has a non-zero chance of disappearing on one side and just reappearing on the other. It has quantum tunneled through a region where, were it a classical particle, it would not be allowed to pass through. So we see this all the time in physics and chemistry. It's not a surprise. What was a surprise was to find it taking place inside living cells. The first people to see quantum tunneling was quantum tunneling of electrons in spectroscopy in the 1960s. Then in the 1980s, a group at Berkeley in California saw quantum tunneling of protons, 2,000 times the mass of an electron, so clearly much more difficult, a heavier particle, but nevertheless quantum tunneling from one part of a molecule to another. And they showed that enzymes make use of this trick in moving particles around. Enzymes essentially are the workhorses of the cell. They break and build other particles, proteins inside the cell. And one of their tricks is to shuffle and move particles around, and they use quantum tunneling to do this part of the time. So that was established in the 1980s. So it's not like a very recent thing. What we're interested in is quantum tunneling in a different mechanism, namely in the hydrogen bonds that hold the strands of DNA together. That's what the new area is that we're looking at.
And so then, in both of these cases, with the robin and the DNA, the idea is that entanglement and tunneling are fundamental features of the world happening all over the place. And then, as you said earlier, it's only natural that through natural selection, evolution would take advantage of these features for reproductive success.
Yeah, but by taking advantage of it, life would have had to evolve the ability for this behavior to take place in cells in a way that it wouldn't normally take place in inanimate matter with that temperature, with that complexity. I mean, the DNA example is that you've got these, the double helix, the strands of DNA is like a twisted ladder. The rungs of the ladder are hydrogen bonds. As far as I'm concerned, those are protons. I don't talk about hydrogen atoms because my background is nuclear physics, so I don't care about the electrons. I leave them for the chemists. I deal with the nucleus of hydrogen, the proton. So this proton can quantum tunnel across from one side to the other. We've published several papers over the last few years, very sophisticated sort of computational chemistry simulations to show that this is very likely to happen. And if the proton quantum tunnels from one strand of DNA to the other, then when the DNA strands unzip in the process of replication, you unzip them and then each one has a copy made of the other one that it attaches to, and you get two double helices. If the proton's in the wrong place in any one of these sites between the two strands, that could lead to a mutation in that base. And so it's important, that life has life evolved the ability to see these quantum effects. The point is that quantum tunneling, quantum entanglement, long-lived quantum coherence is another example in photosynthesis where quantum biologists are interested, should all disappear very, very quickly. Decoherence should kill off any quantumness far more quickly than the processes of life can make use of. And what seems to be happening, this is what really interests me, is the structure of the environment surrounding this quantum system such that it can stave off decoherence, maintain quantum coherence for long enough for it to play a biological functional role. So, the structured environment is what's interesting. And if that is true, then, hey, why not? Life has had billions of years, so it will, any tricks that might have been available to it, it would have finessed over generation after generation after generation. And so those cells where they have been able to maintain quantum effects to give life an advantage will have been the ones that were selected for. So, but it must be something special about life and evolution that allowed it to choose these processes where quantum mechanics can play a role.
So decoherence has come up a couple of times, mainly in the context of the Everettian theory of quantum mechanics, and this being the mechanism of the branching of the many worlds. But I don't think that we've ever gone into much depth into what it really is. And I had been holding off on it because I knew it would come up when we talked about the arrow of time, but maybe now is a good idea to just lay out theoretically what quantum decoherence is, since we've talked about it so much.
Yes, it's a bit like entanglement. It's one of those features of the quantum world that is not taught at a basic level, and I think it's so vitally important that it needs to be. When we teach quantum mechanics to undergraduates in physics or chemistry classes, we tend to deal with very simple, isolated systems, and we solve the Schrodinger equation of quantum mechanics. And so, a particle at some time is behaving in this way, or quantum state is behaving in this way, and you evolve this in time by solving the Schrodinger equation, and you see what it's doing at a later time. And then the standard way we teach quantum mechanics is say, and then we measure it. And the probability of finding a particle, say, in a certain place, or with a certain energy, or with a certain spin, is the numbers, the math gives us that probability. But there's nowhere in the way we teach quantum mechanics how that measurement takes place. What is happening when you open Schrodinger's box with the cat inside, dead and alive at the same time? What is actually happening? So the Everettian view is one that says, right, we've solved the problem. That what is happening is that the quantum state never collapses, but there are all these different options, and when you make a measurement, you are just in the universe where that option is realized, and there's another you. So, but decoherence theory is more general than that. Decoherence is the means by which the environment surrounding a quantum system interacts with it. In a sense, you can say measures it, but interferes with it, or gains information about the system. And it's inevitable that decoherence will take place, because the fact is there is no isolated quantum system in the universe apart from the whole universe itself. So one could imagine some God's eye view outside the universe and say, well, the universe never decoheres, because there's no environment outside it for its information to leak out into. But within the universe, any system we want to know something about inevitably cannot be maintained indefinitely isolated from its environment. Decoherence simply means the leaking out of quantum coherence, something that can be in two places at once, or have more than one energy at the same time, or be spinning up and down at the same time, all the weird stuff that happens in the quantum world. That information leaks out very quickly into the environment. So the environment causes this quantumness to decohere in the same way as a hot cup of coffee in the fridge will leak out its heat. So it's a bit like thermodynamics in the sense that in thermodynamics, heat leaks out from a hot system to a cold. In the quantum world, we talk about quantum coherence leaking out into its environment. We may come to this in a moment, but another way of saying this is that it becomes entangled with its surroundings, entangled with its environment. So decoherence is a universal process. It happens all the time. You prepare a quantum state that starts off isolated from its environment, and inevitably it becomes entangled and decoheres its information into the environment in a one-way process. Do we need Everettian quantum mechanics? Well, the measurement problem, I won't get technical, but I'd suffice to say the measurement problem actually comes in three parts. The first two parts, called the preferred basis and then the collapse of the off-diagonal elements of what's called the density matrix, technical mathematical terms, they're solved by decoherence. You're still left with a final stage of the measurement problem, which is why physicists still worry about the measurement problem, that you can only explain if you plant your flag on a particular interpretation of quantum mechanics. You either say there are many worlds, this is the Everettian view, or you say there are hidden variables, or you say the quantum state undergoes some sort of physical collapse, spontaneous collapse, or you say, I don't care. That's the Copenhagen view. You say, yeah. I don't care. I just want to calculate. I just want to work out the numbers and follow the recipe. So decoherence is as a physical process. It's not controversial anymore. It's been around for 50 years. It's been quantified and formulated, developed mathematically, but it doesn't solve all the mysteries of quantum mechanics. There is still then you're still a requirement to choose an interpretation to explain to us how we observe the quantum world, how we see it, how we bring it into reality.
Hmm. This is orthogonal to the direction in which we've been going, but since you mentioned hidden variables and Copenhagen, I'm wondering if there is a specific interpretation that you put your chips on.
For many years, since I was a grad student, I was never happy with the Copenhagen view. So that's the stand. It's called Copenhagen interpretation because the founding fathers of quantum mechanics worked at Niels Bohr's institute in Copenhagen. So Heisenberg and Pauli and Enrico Fermi and others all spent time there. And it's not really an interpretation. It's a recipe, right? It says quantum mechanics works. The maths are all developed and detailed, and it helps us learn about the quantum world. Without the mathematics of quantum mechanics, we wouldn't have understood the structure of atoms and molecules. We wouldn't have nuclear and particle physics. We wouldn't have developed modern electronics. We wouldn't have developed computers. I wouldn't be talking to you across the internet and so on. So the Copenhagen view is very often some people talk about it as the shut up and calculate interpretation.
Yeah.
The interpretations that I prefer are what are called realist interpretations. Yeah. What they say is that there has to be a theory that tells us how the quantum world does what it does. It's no good saying it does it, I don't care. All I'm interested in is the results of measurements, the results of experiments. I want to know how the atom gets from A to B. It must do it somehow. If I can't decide, that's my problem. Nature doesn't care whether I'm shutting up and calculating or whether I'm racking my brains trying to figure out how it does it in some way. So there are multiple ways of. In fact, I think I tweeted about this today. There's a Twitter account I follow called Physics in History or something like that. Had a very nice summary of about a dozen or so different interpretations. It started with Copenhagen, then it went on to Everettian many worlds, Bohmian hidden variables. I'm agnostic about which of the realist interpretations worked. And the three front runners will be Everettian many worlds, Bohmian or de Broglie-Bohm pilot wave theory or hidden variables, and spontaneous collapse theories. In order of choice, were I allowed to choose which one I want to be the correct one, my preference is Bohmian mechanics, hidden variables.
Okay, interesting.
So yeah, so I mean, Everettian quantum mechanics, I can see the attraction. I'm persuaded by the attraction, but I have that metaphysical mental block about infinite universes that still bugs me.
Yeah, I've done a couple of episodes on many worlds. Tim Maudlin, who's a friend, is very big on Bohmian mechanics. I've done a couple of those, but I haven't done any on spontaneous collapse or Gerard Ramini Weber. But that's coming up in the pipeline. But okay, right. I've mentioned time's arrow a number of times already, so let's get there. And so macroscopically, I mean, we see time as flowing in one direction, namely from past to future. But do you find it useful at all to distinguish between different arrows of time when you talk about this?
There are certainly lots of different arrows of time that at face value don't seem to be connected with each other. There's the arrow of time pointing in the direction of the expansion of the universe. There's the arrow of time that's pointing in the direction of increasing thermodynamic entropy, increasing disorder. Or the Boltzmann arrow of time in statistical mechanics that says it's just statistically inevitable that when you shuffle a pack of cards, they're going to become more disordered, not more ordered. But yeah, there are other arrows of time. There's the arrow of time that tells you that effect follows cause, or that spherical waves are outgoing rather than incoming, and so on. Whether these are all connected or not, I mean, at some fundamental, one would have to assume that they are. But the other option is that there is an arrow of time baked into the universe, and these processes are following, the arrow of time comes first. It's not that the processes come first, giving you an arrow, and then you worry about how to unify the arrows. There's a single arrow of time, and these processes all point in the direction of this arrow. And that's the sort of idea that I'm thinking about.
Hmm.
I'm currently writing a paper with a philosopher of physics, Eddie Chen, in San
Oh,
Diego.
yeah, yeah, yeah.
You know Eddie?
Yeah. I
Yeah.
haven't talked to him yet, but I know that he's been recommended to be on the podcast a number
He's
of
great.
times. He's part of the John Bell Institute, which is
Right.
how I found him.
Yes. Well, he's a collaborator with me on our research program funded by John Templeton Foundation. So we talk a lot. When I was in the US last week. Before I was in the Bay Area, I was down in LA. We had a 2-day workshop at UCLA, organized as part of our research program, and I had a nice long chat with Eddie there, developing some of our ideas along these
Nice.
lines, the arrow of
Yeah,
time.
I think I was hanging out. Well, I was hanging out with who I think is his graduate advisor at Rutgers, Barry Lower, this weekend. So it was
Ah,
funny.
right, okay.
Yeah, that's funny. The only other arrow that I was thinking of is the psychological arrow, that we remember the past
Yeah,
and not the future. But the significant point is that these are all macroscopic arrows pointing in one direction and presumably have some underlying connection. But
yes, yeah.
what does it mean then to say that at the quantum level? So at the macroscopic level, time appears asymmetric for this reason. That's another way of putting it. What does it mean to say that at on quantum scales, time is symmetric? Do you have like the evolution of the Schrodinger equation
Yeah.
in mind?
Yeah. So, well, in fact, I mean, it's symmetric in classical mechanics in just Newtonian equations of motion.
Mm-hmm.
Similarly, they're called time reversal invariant. You switch
Right.
time to minus time. You run the movie backwards down at the microscopic scale, albeit described by classical mechanics. And again, there's no difference. Time, can run forwards or backwards. Down at the quantum scale, you switch time. Time reversal invariance in the quantum world is a little bit more technical because you don't just switch t to minus t. You have to take what's called the complex conjugate of the wave function and so on. But yeah, the fundamental equations of dynamics, and indeed in relativity theory, are time reversal invariant, which means they're symmetric in time. And so the usual argument is, which goes all the way back to the 19th century, something called Loschmidt's paradox, which says, if our fundamental laws of physics are symmetric in time, how do we see an arrow of time? How does this arrow of time that, is so manifest, even whether it's, our memories of the past, but predicting the future, entropy increasing, and so on and so forth. How does that emerge from symmetric fundamental laws? My view, there are others who have thought and written this way. Roger Penrose is one. Lee Smolin is another. My view is that the arrow of time is more fundamental than these time symmetric equations. The arrow of time is baked in to reality. The equations that are time reversal invariant, time symmetric, are approximations because they only describe isolated systems. So this is what leads to the entanglement and decoherence ideas. There is no such thing as a truly isolated system. Yes, if you put a pendulum in a box and in a vacuum and set it swinging, in principle, it'll swing forever if there's no damping. But nothing is completely isolated from its surroundings. At some point, there'll be interaction. Even the cosmic microwave background, will have an effect at some point. So nothing is isolated. Everything is an open system, and therefore there is no such thing as absolutely 100% time reversal invariance anywhere in our universe other than the entire universe itself. I'm not interested in the entire universe itself. I'm interested in being able to say something about some part of the universe. I can't step outside of the universe to talk about it. So for me, that's not interesting. I'm not a cosmologist anyway. But the fact that everything is open means there is always, down at the quantum level, entanglement, decoherence. And that immediately gives us an arrow of time, an arrow pointing in the direction of increasing entanglement, increasing decoherence. So the Schrodinger equation, which is time reversal invariant, is only an approximation because it only describes isolated systems which don't exist in the real world. Does that sound convincing?
It sounds convincing until I start thinking about the different interpretations. So the like many worlds, the Schrodinger equation is all there is really to describe everything, and there is only one system.
Well, it's all there is for the entire universe.
Mm-hmm.
It's not all there is when you describe a system. You know, in Everettian quantum mechanics, you know, you open Schrodinger's box and you make a measurement. You see the alive cat or the dead cat. Before you opened the box, it was both. It was alive and dead. Of course, before it's decohered, before decoherence has taken place, it could be alive, dead at the same time. Decoherence kills off the alive dead at the same time, but you still have the two observable states, the alive and the dead. It's not that before you open the box, it's just your ignorance. Both states exist as far as you're concerned. They're both opening the box, you see an alive cat. There's another you in a parallel universe sees a dead cat. But that measurement process has given you the arrow of time. The Schrodinger equation worked before because it was assuming that the box is isolated from the surroundings. At some point, a measurement has to take place, which is another way of saying all systems are really open systems.
Mm-hmm. And how, though, connecting back to biology, how does this all connect to the arrow of time?
Well, in a paper that we are hoping, I mean, it's been to the publishers, reviewers have got back, we've made some changes, we've, you know, in the process, we've submitted it back. I'm hoping it'll get published sometime soon. This is another paper on the proton tunneling in DNA. A surprising result we found is that in the process of unzipping the two strands of DNA, there's a particular molecule, an amino acid, that seems to do the measuring. It's like opening the box, Schrodinger's cat's box. Until then, the surrounding environment, the water, essentially surrounding the DNA, causes decoherence, but only partial decoherence. So it's not fully decohered. It's quantum, what's called the von Neumann entropy isn't maximum. So there is still quantumness going on there. And the proton can still quantum tunnel from one side to the other. But once it starts unzipping, that proton has to make up its mind, right? You can't be in both states at once the two strands are really separated. The barrier between them is too big. And this inside this enzyme called the helicase, which does the unzipping, it also plays the role of measuring. So if in an Everettian view, for example, it is building in the arrow of time by making a measurement saying that, the proton's on this side. And then Everettian would say, in another universe, that enzyme found the proton on the other strand of DNA. So both exist in different universes. So this quantum measurement is taking place inside living cells all the time. And my argument is that the arrow of time is already there. It's already baked in. And increasing entanglement is the direction in which the arrow is pointing.
I see. So it's kind of like this other arrow that we didn't mention, the direction of wave function collapse.
Exactly.
Or the direction of measurement. So this process sort of imposes the direction of time on the quantum phenomena.
And every interpretation, we'll talk about this quantum arrow of time different ways. The Copenhagen view will just say a measurement is made, right? And what was called unitary dynamics, time reversal invariant Schrodinger equation, you can't use that anymore because you've made a choice. And Everettian will say it's the branching of the many worlds that gives a direction in time. The spontaneous collapse GRW approach says that every now and again the wave function of the system collapses to a particular state that you can't go back, you can't uncollapse, right? So that gives it. So all different interpretations have to have in them built in somewhere this directionality to the arrow of time.
Well, one other dimension of the work being done at Surrey right now involves or that I wanted to ask about involves something called green fluorescent protein. And
Mm.
I'm wondering how it's useful with regard to, well, first I'm wondering what it is, and then how it's useful with regard to coherence and quantum biology and what we've just been
Uh,
discussing.
these fluorescent proteins are a good example of trying to study long-lived quantum coherence, a system that can be in multiple energy states at the same time. The motivation for it is because it's a good model of a more complex system, namely the process of photosynthesis. We know that plants and bacteria photosynthesize, they capture sunlight, they deliver it to the reaction center in the cell. And one of the earliest suggestions in quantum biology is that photosynthesis requires a quantum explanation, namely that photon, that lump of energy, follows multiple routes simultaneously, a bit like the particle going through the famous two-slit experiment in quantum mechanics. It's an interference process that allows that photon to reach its destination with such high efficiency. Without quantum mechanics, it would just be like a pinball, randomly bouncing around inside the cell and more than likely be lost as waste heat. But it doesn't. It coherently reaches its destination. And so quantum coherence in photosynthesis is another thing that is being studied. And the green fluorescent proteins, which you can put them inside in a laboratory in your experiment, zap them with these rapid laser pulses and see how they excite and de-excite, is a means of studying whether quantum coherence can last in biological systems for long enough to have a functional role.
Well, I'd like to finish with just one last question, a more speculative question. But so if you think that understanding the connection between time symmetry and quantum mechanics and biology might point the way to some sort of insight that could better help us understand what distinguishes life from the inanimate, I'm wondering if you think this could have huge implications for how we distinguish or might distinguish upon arriving at or otherwise exploring strange new worlds, alien chemistry from alien life, for instance.
Possibly. I mean, it's sort of, you can go to sort of workshops or talk to other physicists, chemists, biologists, where some of these ideas are talked about. What is it that indicates life? What is the difference between biology and chemistry? Does quantum mechanics play a role? And so, yeah, there is a mix between the two. So the people, for example, in Arizona, Paul Davis's Beyond Center, they're keen on origin of life, foundations of quantum mechanics, quantum biology, and inevitably these areas all get sort of mixed up and shuffled together. But it's sort of still a bit fluffy, and you can talk to hard-nosed, chemists and physicists who will say, no, look, you're trying to find, this is, it's like bordering on vitalism. You're trying to find some magical, quantum mechanics has replaced, the magic pixie dust that sprinkles on inanimate matter and endows it with life. So one has to be careful. And I think certainly with quantum biology, taking small steps, even though it's cool to say quantum mechanics explains the origin of life or quantum mechanics explains consciousness or whatever, I think there's a danger that it can spill over into more speculative areas than we're prepared to be able to stand up and justify just yet, maybe in years to come.
Well, Jim, this has been super fun and a lot of terra incognita for me in the show. So thanks so much for taking the time to have this conversation with me.
My pleasure. It's been good fun.